So this is what I put up last time, which was mistaken. This is the homework due Monday. Right. So let's go back to the regular solids. So we have the groups, finite groups, associated to the regular solids in R3. And the group gamma is going to be a subgroup of SO3. The rotations that preserve rotations preserving the solid S, the regular solid S. So there are 5 regular solids. The tetrahedron, and gamma is of order 12 in this case, as we showed, and we're going to show is isomorphic to A4, permuting the vertices, because there are 4 vertices, so that gives you a subgroup of S4. We're going to show it's the alternating group. Then last time we discussed the octahedron, but it turns out you get the same gamma for the dual solid, which is called the cube. Here gamma is, for both of these, gamma is of order 24, and I'm going to show you today is isomorphic to S4, permuting diagonals of the cube. I'll show you how that works. And for the last time I talked about the icosohedron, which has 20 sides, but today I'll show you also the dodecahedron, which has 12 sides. Gamma has order 60, and I won't prove today that it's the alternating group on 5 letters. That's quite tricky. It happens to be isomorphic to A5, but what 5 things it permutes are hard to write down. But I will show it's a simple group. No non-trivial normal subgroups. So it's our first example of a non-abelian simple group. We have some abelian simple groups. In fact, the only abelian simple groups are the cyclic groups of order P. If you have any abelian group whose order is not a prime, it has non-trivial subgroups and therefore non-trivial normal subgroups, so isn't simple. But if it's of order a prime, then any subgroup is either the trivial group or the entire group, because any element has prime order, or 1. Cyclic of order P. So the only abelian simple groups, we know them, they correspond to the prime numbers. And this is the first non-abelian simple group. And I'll talk a little bit about non-abelian simple groups, but the first one is of order 60. Okay, so let's go through the tetrahedron, because last time we proved that there was a group that permuted the vertices transitively. In this case, there are 1 element E. There are 8 rotations of order 3 fixing a vertex. So each vertex has a little rotation group where you rotate either by 120 degrees or by 240 degrees. Those give 2 different rotations of order 3. And there are 4 vertices, so there are 8 different rotations of order 3, preserving the tetrahedron. And last time I said there are 3 rotations of order 2, which on the vertices switch pairs of vertices. So for example, as a permutation might look like this. Doesn't fix anything, but it switches 2 different pairs of vertices. So it's easy to show you that if I actually have the thing and I can hold it up. So we're going to switch these 2 vertices, and so the 2 vertices here are going to be switched, and the 2 vertices here are going to be switched. So what rotation does that? You take the axis, so rotation is determined by its axis. you take the axis through this edge, the vertices you're going to switch here, and this edge. So you draw the line through the center of this edge and this edge, and you rotate 180 degrees around that axis, like that. And you notice it switches these two vertices and these two vertices. So I'll go backwards with you. Okay? So it's a rotation of order 2, 180 degrees, and through the axis is the midpoint of the edge, is midpoint of edge connecting 1 and 2 to the midpoint of the edge connecting 3 and 4. And for any pairs of vertices, you can draw the axis through the midpoint of the opposite edges. If I took these two, and then I have these two, I draw the axis through here, and rotate 180 degrees around that. So you have to actually do that with a tetrahedron in hand, and you'll see that there are three pairs of opposite midpoints that you can use. That gives you 3 elements of order 2, which is permutations look like this. Now, it's time that we started introducing good notation for permutations, because I'm sick of doing this. This is not the standard notation. This permutation would be denoted, and we're going to have a whole section, a whole lecture just on how to do computations in the symmetric group, but let's get our notation down right. What you do with a permutation, the way you notate it, is you follow where elements go. So this would go like this. I'd notate this permutation as follows. I'd start with a bracket, then I take 1. Then the next thing I put down is where 1 goes. It goes to 2. Okay? Now the next thing I'd put down after 2 is where 2 goes. If it gets back to 1, which it does in this case, you close off the parenthesis like that, which means that this effectively takes 1 to 2, and it takes the last thing here back to the first thing, 1. And then I'd also have 3 going to 4. That's how I'd notate that permutation. Okay? Let's notate another permutation in S4. Let's do the permutation that fixes 4, but that circles the others around. Okay? That would be notated as follows. 1, 2, 3, 4. It takes 1 to 2. It takes 2 to 3. It takes 3 back to 1. And it takes 4 to itself. Get the idea? There's no thought in this. It's just a way of writing down this thing without having to write the numbers twice in a bunch of arrows. Okay? It's a little bit more compact as notation. Let's do another permutation. Let's do a permutation of 5 things. 1, 2, 3, 4, 5. Let's do this permutation. 1 to 2, 2 to 1, 3 to 5, 4 to 3, 5 to 4. That's a good permutation of 5 things. It would be notated like this. 1, 2. See, they have a little L. 1 to 2, 2 goes back to 1. And then 3, 5, 4. Bang. 3 goes to 5. 5 goes to 4. 4 goes back to 3. Okay? So from now on, we're going to notate our permutations this way. So in particular, these rotations of order 3 look like this. 1, 2, 3, 4. 1, 3, 2, 4, because those are the 2 rotations that fix the element 4. And then I'd have things like 1, 2, 3, 4, and 1, 2, 4, 3. And then I'd have 2, 1, 3, 4, and 2, 1, 4, 3. And then I'd have 3, 1, 2, 4, and 3, 1, 4, 2. Those would be my 8 permutations of order 3 in this group of the tetrahedron. And the other elements of order 2, I'd have this one, 1, 3, 2, 4. That would mean switching vertices 1 and 3 and switching vertices 2 and 4. And then finally I'd have 1, 4, 2, 3. Right? And then finally this element would be written 1, 2, 3, 4. Takes 1 to itself, 2 to itself, 3 to itself, and 4 to itself. Is this enough to get the notation settled? We're going to do a lot of computations in the symmetric group, but that's it. Now, the reason that this is the alternating group on 4 letters is you can, first of all, we proved last time it has order 12. You can check that all of these permutations have determinant 1 if you think of them as permutation matrices. So they're all in the alternating group. So whatever this is, it's a subgroup of the alternating group, but it has the same order. Therefore, it's isomorphic to the alternating group. Okay, let's do this one. Last time we did the octahedron. I'll do it for the cube this time. It's a similar argument. The cube has 8 vertices. It has 6 faces. It has, yes, 6 faces. And it has 1, 2, 3, 4, 5, pardon? 12 edges, thank you. The stabilizer of a vertex, gamma sub v, the thing's fixing a vertex. Well, if I fix a vertex, and I take the axis through that vertex, sorry, let's fix a face. It's easier. It's easier to see. Suppose I want to fix this red face. I take the axis through the midpoint of that face and the opposite face, and I have the rotations of order 4 around that axis. Right? So that's it. The fixer of a face, let's do that case. Gamma of a face is of order 4. And 4 times 6, because it permutes the faces transitively, I can take these 4 faces to themselves by rotating around here. And if I want to take the red face to, say, the blue face, I take the axis through these faces and I rotate a 1/4 degree like that. And so I can permute the faces transitively. So that shows the group has order 24. Now, to show that it's a subgroup of S4, I have to give 4 things that it permutes. And I don't have 4 vertices, and I don't have 4 faces, and I don't have 4 edges, like I did for the tetrahedron. So it's not obvious what 4 things it permutes. However, if it takes the cube to itself, it permutes the diagonals that connect opposite vertices. And there are 4 such diagonals, because there are 8 vertices. Right? So it takes those diagonals to themselves. So it gives a permutation of 4 things, because it takes the vertices to themselves. So it preserves a vertex that's opposite a vertex. So this is permuting the diagonals. That gives this as a subgroup of S4, but they have the same order, so I don't have to do any computations. They're isomorphic to S4. And for the icosahedron, yeah,
I'm sorry, it's not totally obvious to me how these diagonals are getting permuted.
Anytime I have a motion that takes the cube to itself, right, it takes the vertices to themselves, so it takes the lines through opposite vertices to lines through opposite vertices, because it preserves the relation of, and there are 4 such lines. So they're permuted whenever I have a motion of the cube. Conversely, if I know what that permutation is, I know where the vertices have gone, or at least where the pairs of opposite vertices are going, but in fact where the vertices have gone. And that, because it's a rotation, and that gives me a map from gamma into S4. They have the same order. They're isomorphic. I'm doing today for the icosahedron. It was easier for me to build. So the icosahedron, instead of the faces being triangles and having 5 triangles around a given vertex, the faces are pentagons, and you have 3 pentagons. Yeah.
Is that an icosahedron or dodecahedron?
This is a dodecahedron. I apologize. The last time I tried to build an icosahedron, and I almost died. Because you have to put 5 triangles around a vertex. So here's 3 pentagons around each vertex. Right? So you have this thing, the dodecahedron, has 12 faces, which are now pentagons. Notice that in the cube, instead of having faces that were triangles, which we had for the octahedron, we have faces which are squares. So here we have 12 faces that are pentagons. We have the number of vertices, sorry, 1, 2, 3, 4. Yeah, the 12 faces. The number of vertices is, what, 20 vertices? I forget how many. 1, 2, 3. That's it, 20 vertices, thank you. And again, 30 edges. Now again, to figure out the group here, we'll figure out the stabilizer of a face. Well, if I want to stabilize a face, I take the axis of rotation through the face and through the opposite face, and then I can rotate around 1/5 of the circle and stabilize this face, and it also stabilizes this face underneath. Okay? And so a stabilizer of a face turns out to have order 5, cyclic of order 5. And 12 times 5 is 60, and that's the order of the group. I can't show you that it's isomorphic to A5 because to give you something that's preserved by A5 in this group is quite complicated. Give you 5 objects that are preserved. Artin gives an example. If you inscribe cubes inside of a dodecahedron, there are 5 cubes inside of this that are taken to each other by rotations. I don't want to even try to draw that. Take a look at the book. I'll just ask you to believe for the moment that it's A5. We don't need that at the moment. What I'm going to show you is that it's a non-abelian simple group. So to do that, we have to figure out what are the conjugacy classes. Okay. Now the 12 faces, I claim, give me 6 cyclic subgroups of order 5. So we're now going to work out the conjugacy classes in gamma. So the faces give 6 subgroups isomorphic to Z mod 5. The reason is that you get the same subgroup of rotations for each pair of opposite faces. So I have 5 rotations around here, and then I have 5 rotations around here, right? So the 12 faces give 6 pairs of opposite faces, 6 subgroups of order 5. So the 6 different subgroups. The only way those subgroups can intersect is in the identity, because the intersection of two distinct subgroups would be a subgroup of both. But a subgroup of a cyclic group of order 5 is either the whole group or the identity element. So they have no intersection but the identity. So these 6 subgroups of order 5 sort of look like this. And you get in each one 4 elements of order 5. The non-identity elements in the group, and they're distinct elements in the group. So that gives 24 elements of order 5. Okay, next step. We have, as I said, 30 edges. Now, if you have an edge, it has an opposite edge. And if you take the axis through the midpoint of that edge, just like we did for the tetrahedron, you can rotate 180 degrees around that axis and preserve the icosahedron. So that's an element of order 2. Right? So you have 30 edges, give 15 different subgroups isomorphic to Z mod 2, because each pair of opposite edges determines the same subgroup. And again, those are distinct groups. They go out. They only intersect in the identity. In a subgroup of order 2, you only have one non-trivial identity element, so you get 15 elements of order 2. And now, when we go to the vertices, if you take a pair of opposite vertices, you can rotate by 120 or 240 degrees. You have rotations of order 3, because you have 3 things coming out of the vertex. So again, the 20 vertices give 10 different subgroups isomorphic to Z mod 3. And each one gives 2 non-trivial elements of order 3. So we get 20 elements of order 3. And so we have the identity element, and then we have all of these elements. Does that exhaust the group? Well, let's add up. Here we get 39 elements. Then we get 20 more, 59 elements, plus the identity. That gives us 60 elements. That's the group. So anything in the group is either an element of order 2, which fixes a pair of opposite edges, an element of order 3, which fixes a pair of opposite vertices, or an element of order 5, which fixes a pair of opposite faces. Okay? So far, so good? Yeah.
Just the E with the spokes coming out of it, I got a little fuzzy.
What I meant was this. I'm drawing the 6 different subgroups inside of G. Here's G. Here is a stabilizer of pair of opposite faces. Now the claim is that the intersection of those 6 different groups is just the identity element. You can't have any of those 2 groups intersecting in more than the identity element. And the reason is that the intersection of those 2 groups would be a subgroup of one of them. But this is a simple group because it has prime order. So it's only subgroups of the whole group or itself. So if the intersection were all of it, it would mean these 2 things were the same. But the stabilizer of this pair of opposite faces is not the same group as the stabilizer of this pair of opposite faces. They do different things. I mean, this one fixes this face and this one fixes this face and this face. So they're not the same group, so they have no intersection. So therefore, there are 5 elements in this. They give 4 elements of order 5. Those are distinct from these 4 elements of order 5, which are distinct from these 4 elements. So the total number is 24. 6 times 4. Okay? You don't have to do that for a subgroup of order 2, because if they don't intersect, I mean, it's just, right? And for an elements of order 3, we'd have 10 different things going off, whatever 10 looks like. And each one contains 2 elements of order 3. So this 20 is 10 times 2. Okay? Now, let's write that down. So we have this 60, because we're going to analyze why this group is simple. We have this 60 written as 1 element of order 1, 15 elements of order 2, 20 elements of order 3, 24 elements of order 5. Now, one possibility, the first thing you might guess is, now you can't have an element of order 2 conjugate to an element of order 3, right? Conjugate elements have the same order. The reason that is true, which you saw in the exam, is that if you have an element which is conjugate to G, say G prime is equal to HG H inverse, and G to the n is equal to the identity element, then if I take G prime to the m, and I write it as HG H inverse times HG H inverse all the way down m times, this is m times, then I can cancel the h and the h inverse all through this to get h g to the m h inverse. And g to the m is the identity, so this is just h inverse, which is just the identity, which shows that the mth power of g prime is the identity. But that shows the order of g prime is less than or equal to the order of g. But then you do the converse, and you show the order of G is less than or equal to the order of G prime, so they're equal. So conjugate elements have the same order. Therefore, the conjugacy classes in G have to be, well, this is a conjugacy class. You have to have a conjugacy class made up of the elements of, this could break into different conjugacy classes, but these things have to break up into conjugacy classes that have nothing to do with these conjugacy classes, etc. Now, sometimes in a group, you get lucky, and the order determines the conjugacy class. So, for example, that can happen. For example, in the symmetric group on 3 letters, we saw we had 6 elements. We had 3 elements of order 2, 2 elements of order 3. The elements of order 2 were all conjugate. The elements of order 3 were all conjugate, so that did it. Conjugacy was determined by the order. Now, is it possible that the conjugacy classes inside of this group are just determined by the orders of the elements? Is it possible that this is the class equation for the group? Like the previous one, was 6 is equal to 1 plus 2 plus 3. That broke down into conjugacy classes. Could there be 4 conjugacy classes, the identity element, all the elements of order 2, all the elements of order 3, and all the elements of order 5? Is that possible? No, it is not possible. Why? Because the order of a conjugacy class of G is equal to the order of G divided by the order of the centralizer of the element last time. So divides the order of G. And there's a problem here. Namely, 15 divides 60, 20 divides 60, but 24 does not divide 60. So it's possible that all the elements of order 2 are in one conjugacy class. It's possible that all the elements of order 3 are in one conjugacy class, but this has to be at least 2 classes, because 24 doesn't divide 60. The elements of order 5 are not all conjugate. Now what happens, and I'm going to show you that geometrically, it's totally cool, it's the simplest thing possible, is, given the class equation, this is a conjugacy class, this is a conjugacy class, this is a conjugacy class, and this breaks up into 2 conjugacy classes. There are 2 conjugacy classes of elements of order 5, and I'm going to show them to you here. Let's first prove that the elements of order 2 are all conjugate. So the elements of order 2, we remember, come from taking the midpoints through opposite edges and rotating 180 degrees. Now suppose I had one element of order 2, and you gave me another element of order 2, maybe this edge and this edge, and you wanted to conjugate the rotation around this edge of 180 degrees to the rotation around this edge of 180 degrees. How do you imagine you'd do that? Remember, these are the things fixing an edge, right? And the edges are permuted how by the group? Transitively. So if I could find an element in the group that took this edge to this edge, and I can, it seems reasonable that that element would conjugate the rotation fixing this edge to the rotation fixing this edge. And in fact, that happens. You have to check that. So these are all conjugate by elements permuting the edges transitively. I'm going to write that out for you. So here, let's write it out. Why is that conjugate? Say G squared is equal to identity is element fixing pair of edges, we'll call opposite edges, I don't know, we'll call it 1, 2, something like that. Opposite edges, 1 and 2. Okay? And we have another pair of opposite edges, 3 and 4. G prime is element fixing the pair of edges 3 and 4. Okay? Let H in G take the edge 1 to the edge 3. We know we can do that because the group permutes the edges transitively. For example, these edges happen to be centered around this vertex. So I would just take the rotation of 1/5 the circle that takes those edges. But even any pair of edges can be taken one to another by some rotation. So find an H that takes the edge 1 to the edge 3. Then it takes the edge 2 to the edge 4 because it preserves the dodecahedron. So once I know where an edge goes, I know where its opposite edge goes. Opposite is preserved. Okay. And then I claim, let's hope I get this right, that G is equal to H G prime H inverse. No, other way around. G prime is this, I believe. Let's check. Well, we have to see that it fixes the edges 3 and 4. So let's apply this to the edge 3. H takes the edge 1 to the edge 3, so H inverse takes the edge 3 to the edge 1. G fixes the edge 1, so it's H of 1, and H takes 1 back to the edge 3. So this element, whatever it is, fixes the edge 3. It also fixes the edge 4, and there's a unique element of order 2 that fixes the edges 3 and 4, which is our element G prime. So here's our conjugation. Okay, now you'd say, well, why doesn't that prove that all these elements of order 5 are conjugate, or all these elements of order 3 are conjugate? Because I can permute the faces transitively, and I can permute the vertices transitively. Why doesn't that permute all these elements to one to another? Well, the same argument that I just gave you there for the fixers of edges will show you that these 6 subgroups are all conjugate inside of G. In gamma, I'm sorry. And likewise, these 10 subgroups are conjugate in gamma. Because if I want to conjugate the subgroup fixing this vertex and this vertex, this subgroup of order 3, into the subgroup fixing this vertex and this vertex, I just take a transformation that takes this vertex to this vertex. Good. Sound good? But that doesn't imply that the elements are, so these 4 elements are conjugate to these 4 elements in some order, but we don't know that I can take any element here to any element there. What's peculiar about a group of order 2 is that once the subgroups are conjugate, the non-trivial elements are conjugate. But in a group of order 5 or a group of order 3, that doesn't compute. Now it turns out that not only are these subgroups of order 3 conjugate, but you can take any element in this subgroup to any element in this subgroup, so that these 20 elements of order 3 are actually conjugate. And I have to prove that to you. And let's see if I can do that. Yeah. Let's see. Okay. We're going to take this group that does a clockwise rotation around this vertex of order 3. So if you take one element of order 3, that's, the point is, I got it. You can actually make a transformation that takes this vertex into this vertex, like that. And if you conjugate by that, it conjugates around the 2 elements in the subgroup. Namely, as long as I prove that this element is conjugate to this element, and I know it's conjugate to something in this group, but on the other hand, each pair of elements in the subgroup is conjugate, not by an element in the subgroup, but by a different element. And when you actually take the transformation that switches these 2 vertices, and you know there is such a transformation because it produces it transitively, it has the effect of conjugating one rotation into the other. You have to believe me on that. So that, in fact, these 20 elements are all conjugate. However, if you do the same thing for the elements of order 5, so here we know that this subgroup is conjugate to this subgroup, etc. But which elements of this subgroup of order 5 are actually conjugate to each other? We only have one thing that we can use. We can take this face to this face, like that, and see what it does to rotation. And it turns out it takes a rotation into its inverse rotation when you conjugate by that. So in each of these subgroups, an element G is conjugate to G inverse, which is G to the 4th, but not to these 2 elements. So in each one of these subgroups, 2 elements are conjugate to each other, and 2 elements are, and the G squared and G to the cubed are conjugate to each other. And so that breaks this set of 24 elements into 2 sets. In each group, we get 2 that are conjugate to 2 in here, 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 that are conjugate to 2 in here. That's 12, and 2 others. And that's the breakup of this 24 elements of order 5 into 2 conjugacy classes of order 12. And they're the rotations by just a fifth of the circle in either the positive or negative direction. So this is rotations by 2 pi over 5 plus or minus 2 phi over 5. And these are the rotations by plus or minus 4 pi over 5. Okay, that being the case, this geometric argument about transitivity of action and following how things conjugate gives us the class equation. And we see that we have 5 conjugacy classes of size 1, 15, 20, 12, and 12. If you add this all up, you get to 60 elements. Now, imagine that now we're going to prove that G is simple. Proposition. Gamma is a simple group. Proof. Let H be a normal subgroup of gamma with H not equal to the identity. Then I claim, since G inverse is equal to H for all G, that's the definition of what a normal subgroup is, H is a union of conjugacy classes in G. If you have one element in H, you have to have all the conjugate elements in H because of this. Agreed? Okay, so then I have to figure out what could be the order of H. So I have to put together a subset of these numbers that adds up to the order of H. So the order of H is equal to 1 plus sum of the terms above. Maybe it could be 1 plus 15, or 1 plus 20, or 1 plus 12 plus 15, something like that. But, and here's the kicker, no combination of these terms, except for all of them, divides 60. Except all terms divides the order of G. You can't select the subset and add up to something. Well, I mean, it's pretty clear. I mean, once you use 20 and 1, the only divisor of G bigger than 21 is 30. Right? So you can't get to 30. And so the other possible, the divisors of 60, you get the big divisors of 60, you get 30, you get 20, and then what, 15? Yeah, but then we have to be, the number is bigger than 12 because it has to be 1 plus some of the terms above. So it's at least 13. So the only possible divisors we have yet to hit are 15, 20, and 30, and there's no way of putting those together to get 15, 20, or 30. Therefore, they're the only subgroup which could be a union of conjugacy classes and is not the identity is the full group. Therefore, it's simple. Is that nice? It's a striking argument. Usually you don't want to have to enumerate all the conjugacy classes, but in this case we can. By the way, those of you who want to try your mettle on the new notation for the alternating group, in our notation for permutations, you'll find that G, which is 1, 2, 3, 4, 5, and G prime, which is G squared, which is 1, 3, 5, 2, 4, are conjugate in S5, but not in A5. And those represent the two different conjugacy classes of order 5 in the group of the icosahedron. We haven't yet proved the group of the icosahedron or the dodecahedron is the same as A5, but in our permutation terms, here are two different elements of order 5 in the symmetric group. They're both in the alternating group. They're both in A5. They're conjugate in this larger group, but not in the smaller group. Okay, let me tell you a little bit about finite simple groups, and then I'm going to go on and do one more thing today with the class equation. Okay, so the finite simple groups finite simple groups is one of the great tales of 20th century mathematics. We now have a list of all of them. So it's an infinite list, but it's a list. So they start out with A5. And then it turns out that all the alternating groups beyond A5 are simple. And I can give you some other examples of finite simple groups. So if you take the group SL2 of P, so those are the 2 by 2 matrices over the field of P elements. So this is, maybe we would write it like this. Sorry. Of determinant 1. That's not a simple group because it contains the identity and minus the identity, and that forms a normal subgroup. But if you form the quotient by that normal subgroup, is simple for all primes at least 5. There are always a couple of low cases that you have to exclude. So what's the order of this group? Well, we saw that the order of GL2 was the number of bases, which was p squared minus 1 times p squared minus p, bases of z mod p squared. And SL2 is a subgroup of this group consisting of the elements of determinant 1. The determinant maps the group GL2 of z mod pz surjectively onto z mod pz star. You can find a matrix of any non-zero determinant. That means the things of non-zero determinant. And this group has order p minus 1. Right? They're p minus 1 non-zero things. So the kernel of this map, which is SL2, has order, the order of GL2 divided by p minus 1. So the order of this group, SL2, is p squared minus 1 times p. Because if I divide this by p minus 1, I just get p. And then I don't want SL2, but I want to divide out by this subgroup of order 2. So the order of this group is p squared minus 1 times p divided by 2. Okay? The order of this group, by the way, is n factorial over 2. So let's compute a few of these just to see what we get. For p equal 5, I get 5 times 24 over 2, 5 times 12. So this group has order 60 for p equal 5. And you might not be surprised to find out that it's isomorphic to this group. This group has order 60. This group has order 360. Okay? What about the next case? P equals 7. The group has order 7 times 48 over 2. 7 times 24, which is 168. That turns out to be the next smallest non-abelian simple group, order 168. So here's an infinite chain of things. Here's another infinite chain. Okay? So mathematicians at the beginning of the 20th century began to make these infinite chains and find more and more finite simple groups. And eventually they produced a method. There was a great mathematician named Claude Chevalley who at the end of the 1950s came up with a method to produce a whole list of groups of this type. They're called finite groups of Lie type because they're like Lie groups. So you can also do this for SL3 and SL4. I should tell you that. Okay. And people wondered whether that list was complete. And it wasn't complete because in the middle of the 19th century, a French mathematician by the name of Mathieu had described 4 rather bizarre permutation groups called the Mathieu groups. They permuted 11 letters and 12 letters and 23 letters and 24 letters. So they were subgroups of S11 and S12, which were not on Chevalley's list. So those were called sporadic groups. And then everyone thought they were about done, and then the computer discovered another sporadic group. And then they started discovering other sporadic groups on the computer until they finally found that group I told you about last time called the monster group, which has order 10 to the 47th. And it really wasn't discovered on the computer. You can't write that group down, but its conjugacy classes were in some sense understood on the computer. And recently, and when I mean recently, I mean 10 years ago, it was proved that the lists of groups that Chevrolet had discovered, plus 24 sporadic groups that had been basically discovered on the computer, comprise the full list of finite simple groups. It's one of the great triumphs of our century in mathematics. I'm going to bring you in a book next time called The Atlas of Finite Groups, which gives all kinds of information about the finite simple groups. You can't give them all because they're an infinite number. You couldn't even give all the information about the alternating groups. But what it does is it gives information about enough alternating groups so you start to see the general pattern. And likewise, enough in this chain. So you now know the first finite simple group. Now, last time I showed you that if you had a group of prime power order, it had a non-trivial center. So I'm going to recall that and do one more thing, and we're done today. The center of G is not equal to the identity element. And the proof goes like this. Consider the class equation. The order of G, which is p to the n, is equal to 1, the order of the conjugacy class of the identity, plus the sum, the order of G over the centralizer of G. This is G not equal to the identity conjugacy classes. So, if all of these numbers are, if Zg is not equal to G for all G not equal to the identity, then the order of G over the order of Zg is divisible by P for all these terms. Because this is some power of P, this is some smaller power of P, so you're left with a power of P dividing the quotient. But that's ridiculous, because that would say that P to the n is 1 plus a number divisible by P. Because the sum of numbers divisible by P is itself divisible by P. And that's ridiculous. This is divisible by P, this is divisible by P, this is remainder 1 when divided by P. So that's a contradiction. Consequently, one of these terms at least has to have the order of the centralizer equal to the order of G. And such an element is in the center. Hence, Zg is equal to G for some G not equal to the identity, and G is therefore in the center. So the center of a group of prime power order is non-trivial. Let's push that a little harder. Corollary, if the order of G is equal to P, G is cyclic. If the order of G is equal to P squared, G is abelian. So for small powers of P, we can say more than it has a center. The whole group commutes with itself. Well, we've already done this. If you have a group of order P and you take any non-identity element, it generates the group. Generated by any G not equal to the identity. That we know. So now we have to prove this abelian business. Well, it has a non-trivial center. Proof. The center of G is not equal to the identity, so has order P or P squared, because those are the only two divisors of P squared. If the center has order P squared, we are done. Correct? Because if the center has order P squared, that says everything commutes with everything, we're done. If not, take an element if the center of G has order P, take an element in G which is not in the center and consider the centralizer of the element G. Well, that certainly contains the center. This is the stuff that commutes with everything, so it certainly commutes with G. But it also contains the element G, because G commutes with itself. And this group is strictly larger than the center. Okay? Well, if this group had order p, if this group is strictly larger, this now has order p squared. If this group has order p squared, that's the whole group, which implies that G is in the center of G, because its centralizer is the entire group. But that contradicts the fact that G was not in the center of G. So the hypothesis that the center had order p is impossible, so therefore the center has order p squared, and we're done. Now you might think, because I haven't shown you otherwise, that a group of prime power order is always abelian. Maybe this is very weak. Maybe any group of order p cubed is abelian. So to show you that this is a good theorem, this is actually meaningful, I have to show you a group of order p cubed that's not abelian. So here it is. A non-abelian group of order p cubed. Take G, a subgroup of GL3 of P. See, it's so useful now that we have these matrices groups. And it's the group consisting of the matrices that look like this. I claim that's a subgroup because if you multiply matrices like this, you get another one. It's closed under multiplication and inversion. It has clearly order p cubed because you have p choices for x, p choices for y, and p choices for z. And you can check by multiplication it's non-abelian. In fact, the center of G has order p and consists of the matrices that look like this, where x and y are both 0. That's a good exercise to see a non-abelian group of order p cubed. But if it was you see, this argument shows the center couldn't have order p squared, because if the center had order p squared, we'd do the same argument here and show that the whole group was the center. So here, if it's not going to have order p squared, but it's non-trivial, it has to have order p. Here's an example of a non-abelian group of order p cubed where the center has order p. Good. So we're really getting into the real stuff now. Pretty soon we'll actually know how to work in the symmetric group. Have a nice weekend.